You ever get that feeling when you're listening to music that there's some kind of hidden logic to it all? Well, it turns out you're not wrong. Music is actually written in a secret mathematical language, and today we're going to crack that code. It's a pretty wild idea, but it's not new. The great astronomer Galileo believed the entire universe is written in the language of math. So that kind of sets the stage for us, doesn't it? If the whole universe is a book of math, maybe music is one of its most beautiful chapters. So what on earth do Bach, secret codes, and donuts have in common? I know, it sounds like the beginning of a really weird joke, but stick with me, because the answer reveals this incredible, hidden connection that might just change the way you hear music forever. Let's find out how they all link up. All right, first up, Bach's secret number. We're starting our journey with the one and only Johann Sebastian Bach, who wasn't just a composer, he was a master of hiding secret codes and messages in his music. So check this out. Bach actually left a musical signature in his work. In Old German notation, the notes B flat, A, C, and B natural, while they were spelled B, A, C, H. He could literally sign his name right in the middle of a piece of music. How cool is that? But he didn't stop there. Oh no. He went even deeper, using this ancient practice called gematria. It's basically a system where letters are assigned a number. And when you do that for his name, B is 2, A is 1, C is 3, and H is 8, you add them all up and what do you get? His secret number, 14. And once you see the number 14, you start seeing it everywhere in Bach's life. It's kind of wild. He actually waited to join a prestigious scientific society just so he could be its 14th member. And his final, unfinished masterpiece, The Art of the Fugue, you guessed it, it has 14 fugues. Coincidence? Not a chance. Not with a mind like Bach's. So this raises a huge question, right? Was this all just an elaborate game for him, a fun little puzzle? Or was he tapping into something deeper, some kind of fundamental reality where music and math aren't separate things at all, but maybe two sides of the very same coin? To figure that out, we gotta go way back. Okay, our next stop, music by the numbers. Because long before Bach was hiding codes in his fugues, the ancient Greeks had already figured out that there's a powerful link between the sounds we find beautiful and, well, simple numbers. You've probably heard of Pythagoras from your math class, right? The triangle guy? Well, he discovered that musical harmony isn't just some magic, fuzzy feeling. It's math. The sounds that we find pleasing, like an octave or a perfect fifth, they correspond to these beautifully simple integer ratios. An octave is a perfect 2-to-1. A fifth is 3-to-2. Suddenly, harmony wasn't just a feeling, it was something you could measure. And it's not just about the pitch. Rhythm is pure math, too. Think about it. A whole note, a half note, a quarter note. It's just a system of fractions, right? Simple division. But all of this is kind of like musical arithmetic. To really see the hidden geometry of music, we're going to need a whole new kind of math. Which brings us to part 3, a new mathematical language. Yeah, the Pythagorean ratios, that's the arithmetic. But to see the geometry, we need a language that's all about connections. And that language is called graph theory. It was actually born from a super famous old puzzle about a town called Königsberg that had 7 bridges. The question was, could you walk through the town and cross every single bridge exactly once? People were stumped. Then along comes the brilliant mathematician Leonhard Euler. He realized the layout of the town didn't matter. What mattered were the connections. So he turned the whole map into a simple network of dots, or nodes, and lines, or edges. And just like that, he solved it. And that's the real power of graph theory. It helps us see the true underlying structure of something. I mean, look at these two graphs. They look totally different, right? A tangled mess versus a neat little square. But to a mathematician, they're exactly the same. Why? Because the connections between the dots are identical. It's all about the relationships, not how it's drawn on the page. Okay, and this way of thinking brings us to a field called topology. And finally, to the donut. In topology, you can think of it as geometry on a flexible rubber sheet. A coffee cup and a donut are considered the exact same shape. It sounds crazy, but you can smoothly squish and stretch a coffee cup into a donut shape without ripping it. Why? Because they both have exactly one hole. And this shape, the donut, or a torus if you want to be fancy, is going to be absolutely crucial. All right, section 4, the network of tones. We have all our pieces on the board now. We've got music's numbers, we've got the idea of networks, and we've got the donut. So let's put it all together and finally reveal the hidden shape of music. Musicians, you'll recognize this right away. This is the circle of fifths. It's a really basic musical graph. It just arranges the 12 notes we use in Western music in a circle, where each step you take is a perfect fifth. It's a handy map, for sure, but we can go so much deeper. And this is where it gets really interesting. This is called the Tonnetz, which just means network of tones. It's a way more powerful map. Instead of just one relationship, the fifth, it maps 3 key relationships: major thirds, minor thirds, and fifths. And when you lay it out like this, something amazing happens. Every single major and minor chord forms a perfect, neat little triangle on this grid. But here's the thing. This flat map has a secret. Remember, our musical system only has 12 notes, right? So the pattern on this grid has to repeat. If you go off the edge on the right side, you just reappear on the left. And if you go off the top, you pop back up at the bottom. The edges, they wrap around. And what shape do you get when you connect the opposite sides of a rectangle like that? You get a donut, a torus. This is it. This is the hidden shape of music, a single, perfect geometric object that contains all of the complex relationships of Western harmony. And it's not just a pretty picture. The chord progressions that sound the most pleasing, the ones that feel so natural to our ears, they are literally the shortest, most efficient paths you can take on the surface of this donut. Moving from one chord to the next is just a simple flip or a slide to the triangle right next to it. It's perfect. Okay, last section, an exercise of the soul. So, why? Why on earth does our system of musical harmony map so perfectly onto this one elegant geometric shape? What does it all mean? Well, a music theorist named Hugo Riemann had a fascinating idea about this. He argued that this whole structure isn't some cosmic accident, it's a reflection of how our own minds work. Our brains are basically wired to find and appreciate simple, elegant, efficient patterns. The torus is the most efficient map possible, what he called the principle of greatest economy. Maybe we find music beautiful because, on a deep level, it's just so logically elegant. And the philosopher Leibniz put it even more poetically. He said that music is a hidden exercise in arithmetic of a mind unconscious of its counting. Think about that. When we're listening to music, when we're lost in it, our soul is unconsciously doing math. We are sensing this deep geometric order, this perfection, without even knowing it. You don't need to know a thing about a torus to feel it. So that leaves us with one last, kind of mind-blowing thought to chew on. If music perfectly mirrors these elegant mathematical forms, and if Galileo was right that the universe itself is written in the language of math, then is it possible that when we are truly moved by a piece of music, what we're actually doing is sensing the underlying harmony of the universe itself? A little glimpse of the code that writes reality.